The recording. Perfect. Yes.
Yeah.
Exactly. Thank you very much for starting the recording. Thank you very much for giving me the opportunity to give the first talk in this series. So the series is fairly broad and covers a lot of topics. And I only have this one talk, so I want to focus a bit on two papers, the GCT1 and GCT2 papers that describe the approach of geometric complexity theory. But as I said, the lecture series is broader than this. So the separation of complexity classes like P and NP is one of the most fundamental open problems at the intersection of theoretical computer science and mathematics. And there are few techniques to resolve this conjecture. And one of the main obstacles is the Rasparov-Rudich natural proofs barrier. And in 2001, this paper, Geometric Complexity Theory 1, was published by Mulmuley and Sohony, in which they describe a method that could potentially break this barrier. And I want to tell you today about this method. And so this method is built on Valiant's algebraic complexity theory framework from 1979 and is inspired by Mulmuley's earlier geometric result that P is not equal to NC in an algebraic model. And so the approach defines what is border complexity, and I will define also, I will be carefully defining that. This is independently at exactly the same time also defined by Burgesser. So Mulmuley and Sohony's intuition is this. Do you actually, you probably see my, or hopefully see my cursor, my mouse here. Otherwise it's going to be, otherwise you just tell me. So it's inspired by this geometric result. We do, perfect. While Burgesser's is also inspired by geometric papers, but it's about those papers about tensors and matrix multiplication. So results by Bini and Lehmkuhl and Dickdijk. So it's that already says that it's probably very natural to define border complexity. Now then, the Geometric Complexity Theory 1 paper goes further and proposes to prove lower bounds using representation theory. And that is also developed further in Geometric Complexity Theory 2. All right, so I want to talk about these 5 sections. And having these sections, so there's a very short summary after the end of each section. So if you get lost, that every section is another starting point for you to start listening again, because the topics are rather different from each other. Okay, let's start with the determinate versus permanent. So it's a classical start in 1979, where Valiant proved that the determinant can actually be used as a computational model, as a machine model in a sense, right? You have a multivariate polynomial, a polynomial in several variables that always can be written as a determinant of a square matrix whose entries are polynomials of degree at most 1. Like for example, this one here, polynomial h is like this polynomial here is a specific determinant. It's a determinant of a matrix whose entries are linear polynomials. And you can now define the required dimension of this matrix and call it the determinantal complexity, DC, of the polynomial. So this specific polynomial here, y plus 2x plus xz plus 2xy minus x squared z, this one has a determinantal complexity of at most 3, because we find a 3×3 matrix whose determinant is this polynomial. And in fact, in this case, it's easy to see that this is equal to 3 because the polynomial has a degree 3. And with a 2×2 matrix with linear entries, you can never get a degree 3. Right? So this is the determinantal complexity of this polynomial is exactly 3. And one can then define a complexity class. It's the class VBP, I want to call it in this talk. Those are the things that are easy to compute in this model of computation. It's defined of all the sequences of polynomials. This is a sequence of polynomials HM with polynomially bounded determinantal complexity. So you think of a sequence of polynomials, and each polynomial now has a certain determinantal complexity, and this gives you a sequence of natural numbers, right? And that sequence of natural numbers should be bounded from above by a polynomial. Yeah. So one of the problems of this talk is that polynomial is something that happens to it happens to mean several things. Right? So it's polynomially bounded, and then polynomials are the things that we want to compute, and then there will be other polynomials as well. But that is just one of the problems of the names here, right? But please try to not get confused by that. Okay, so VBP is, let me just tell you some things that are in VBP. So for example, the determinant as a sequence of polynomials is the determinant that M is equal to the sum over all permutations on M symbols. So this is a symmetric group on M symbols. This is the sign of pi, and this is the product I equals 1 up to M of xi pi of I, which is the determinant of this matrix here. And the entries are just x11 up to xmm. This is in VBP because the determinantal complexity of the determinant polynomial is exactly M, and M is just a polynomial in M, right? This is linear. And a different example is like the product x1 up to xm. This is the determinant of a diagonal matrix, right? So this is in VBP because the determinantal complexity is equal to M. But things get more complicated if you do other things. Like, for example, this is the power sum polynomial, and its determinantal complexity is quadratic. Like it's M, it's at most M times M minus 1 plus 1. This has been proved by Valiant with variance construction. So for example, you get the third power sum polynomial here is the determinant of this matrix. And you see, it's not always the case that the entries here are homogeneous. They sometimes do have some constants, right? The constants do appear in this model of computation, and that will be important later on. And so its counterpart is the hard polynomial. So the determinant is easy to compute, and now the permanent is difficult to compute. The permanent is exactly the same polynomial, but without the sign. It's exactly the determinant, but the sign is missing. And now that should be a very hard to compute polynomial. So if you set the variables to 0 or 1, then it counts the number of perfect matchings in a bipartite graph, or it counts the number of cycle covers in a directed graph. And it also has applications in theoretical physics. So I'm not a physicist, so I will not discuss that. And as a function, it's also sharp P-complete. So we expect this to be very, very difficult to compute. And Valiant's theorem that everything can be written as a determinant also holds for the permanent. Every polynomial can be written as a permanent of a matrix with linear entries. And you can define the permanental complexity, like PC, of your polynomial. It's the smallest smallest size of a matrix, so that the permanent is your polynomial. And the class VNP is now are the sequences of polynomials where the permanental complexity is polynomially bounded. Right? So you have determinantal complexity and permanental complexity. And are those the same? Why, the permanental complexity of the determinant is indeed polynomially bounded. And this means that VBP is a subset of VNP. But the other direction is, of course, not known as the wide open conjecture. This is the determinant versus permanent conjecture, that VBP is not equal to VNP, or equivalently, that the determinantal complexity of the permanent is not polynomially bounded. So you do this. If this is over characteristic 2, then of course there's no difference between the two polynomials, because -1 is equal to +1. The signs will not play any role, but you can replace the permanent by the Hamiltonian cycle polynomial. I will keep the permanent in this talk, because we will be doing everything over the complex numbers anyway. So the connections to Boolean complexity are that if you want to separate this, which is still wide open, it's actually easier than separating classes in Boolean complexity. So if P/poly is not equal to NP/poly implies actually our conjecture, variance conjecture, over finite fields and also over the complex numbers, assuming the generalized Riemann hypothesis. And this is just a non-uniform version of P versus NP. It's widely believed that this is true, because if not, then the polynomial hierarchy would collapse, and MA would be AM would be MA, right? So that is widely disbelieved. So therefore, this should be, this is a non-uniform version of P is not equal to NP, and it is widely believed. So we also do widely believe that these two classes are different. Yeah, so this is a summary slide here. So if the polynomial hierarchy does not collapse, and we assume the generalized Riemann hypothesis, then we do have that these two classes are not the same. And so one nice thing, or maybe just a remark here, that this nice model of determinants, it replaces having to deal with Turing machines. We only deal with determinants now, and there's of course hope that one could understand determinants much better than Turing machines. I want to talk about other models, algebraic models of computation, because it seems like the determinant is not exactly the most suitable for geometric complexity theory. So I want to take some time actually to discuss some other models, algebraic models of computation. So the most well-known is the algebraic circuits, where you have an directed acyclic graph. The leaves are labeled with degree 1 polynomials, and the inner nodes are called gates, and they are labeled with plus and multiplication. Certainly, yeah, every algebraic circuit computes some polynomial by just induction over the circuit structure. And so the example on the left computes exactly this polynomial here, right? Where x1 times x2, you square it, you add the 3, you take x1 times x2, you add this 2 plus x1, and then you multiply them, right? So it gives you this polynomial here. Of course, every polynomial can also be computed by some algebraic circuit, but you can just do it monomial, each monomial on its own, for example. And now the size is the number of gates in the circuit, and you can define an algebraic circuit complexity as the size of the smallest algebraic circuit computing H. And this gives rise to a class VP, consists of all the sequences of polynomials with polynomially bounded circuit complexity and a polynomially bounded degree. So yeah, during this talk, I will sometimes drop this requirement of the degree because I don't want to focus too much on the degree. If you think at some point you also have to put some degree requirements, you just put the degree requirement. It's not so crucial here at the moment. Yeah, for example, the determinant has small circuits. That's actually not completely obvious. An algebraic formula is now an algebraic circuit whose graph is a tree, like this one here. And you can define now an algebraic formula complexity, and again define a class that consists of the sequences of polynomials where this complexity is polynomially bounded. Right. So now we have seen actually 4 different measures of complexity, and the definitions of these classes are always consist of all the sequences of polynomials where the complexity is polynomially bounded. And we get 3 different classes. VVP was the determinantal complexity was polynomially bounded. The circuits give you VP, and the formulas give you VF, and they sit inside each other. It's not 100% obvious that they sit inside each other. And they all sit in the bigger class VNP. And so the 3 on the left-hand side are the classes of efficient algebraic computation. And this one is some equivalent of NP or sharp P, if you want to. And the 3 on the left, they actually do coincide if you allow quasi-polynomial complexity instead of just polynomial complexity. So they will be very difficult to separate. Yeah, just for reference, so if you're searching the literature, then these classes do have also some other names. So VF also goes under the name VPE, and VBP has a lot of different names because also has been rediscovered, and the equivalences have been proved. And now variance conjecture it can actually mean any of the 3. You want to separate VNP from any of these 3 classes, because Variant in his original paper is not so completely clear about the distinction of these 3. Also, I mean, there's no real reason to actually be so picky about which one you take. I want to say something about complete polynomials, because this will be important in a minute. So let's go back to our example. The polynomial H here is the determinant of this specific matrix. And that's, you should think of this actually as an evaluation, or also called a projection, of the determinant polynomial. So the determinant polynomial we've seen is this polynomial. And now you evaluate this polynomial at some point here. And those are, yeah, the polynomials here are like linear polynomials. So that 3 is just a polynomial in 9 variables, and you evaluate it at this vector here. And it gives you H. So it's a different way of thinking about this, but it allows you to define a lot of complexity classes and also define what is completeness of polynomials. So in exactly the same way as for determinantal complexity and for permanental complexity, we can define for some sequence of polynomials the C complexity, like not just determinantal or permanental complexity. You can do this for all sequences of polynomials. So the complexity of some polynomial H is just the smallest n, such that H is a projection of Cn. exactly as for determinant and permanent. And you get a corresponding complexity class. There's a sequences of polynomials where this complexity is polynomially bounded. And we say that the Cn is now complete for that class. So the determinant is VBP complete, the permanent is VNP complete, and we will see some more complete polynomials now on the next slide. For example, we need something that's complete for VF, and indeed we can get something that's VF complete. It's the 3×3 iterated matrix multiplication polynomial. It's a homogeneous polynomial, a degree n in 9 times n variables. So you take 3×3 matrices with variables in it, right? So new variables, 9 times n many. You take these 3×3 matrices, you multiply them up, you take the 1, 1 entry of that. That's a polynomial of degree n, and it has 9 times n variables. And that's complete for VF. And instead of the 1, 1 entry, some people take the trace because they think the algebraic properties are nicer. I personally now found some reasons to actually do like the 1, 1 entry of in these models. And now VBP also has several complete polynomials. It's a determinant, but it's also the iterated matrix multiplication n matrices that are all n by n. And you can here take the 1, 1 entry or the trace, or you can take the trace of a power of a matrix or the 1, 1 entry of that. So these are all different complete polynomials for VBP. So it has a lot of different ones. And for VP, it's a more difficult and subtle thing. But you can find complete polynomials as well here for VP. But I want to focus a bit on VBP because it seems to be the most natural one to focus on. And I want to rewrite this. I want to homogenize this. So I want to have a homogeneous model of computation here. So it works as follows. You have a polynomial. H is a homogeneous degree D polynomial. Now, the homogeneous iterated matrix multiplication complexity, so I call it HIMMC, but you should probably get a better name because it's the same as the homogeneous algebraic branching program width. That is just defined as the smallest n such that there exists homogeneous linear polynomials Lijk, or sorry for that, Lijk that have the property that if you take the product of these matrices and the 1, 1 entry, you get your polynomial. But now, so the important thing here is that this is very different from the other models of computations that we had before. Because here, if you're computing a degree D polynomial, then you know the number of matrices will be exactly D matrices, because the degree says what is the number of matrices. And now it's just about how large do I have to make these matrices. And the entries are all homogeneous. So there are homogeneous means homogeneous linear is there are no constants in these linear polynomials here. And that makes it much easier to actually go to geometric complexity theory. And yeah, the original approach is about determinant versus permanent, but this one here is, I think, it resolves a lot of issues that the original approach actually had. Yeah, so let me just say, this is the important thing here. If you have a sequence of polynomials, homogeneous polynomials, then it's they are in VBP if this complexity, this HIMMC, is polynomially bounded. So HIMMC also describes precisely VBP. Note that this is only defined here for homogeneous polynomials. So you could study, for example, the permanent, the HIMMC of the permanent. Yeah, you can also take the trace. Yeah, just a remark. You can also take the trace if you want to, but there are some subtle issues if you take the trace, and there are some other ways of doing it. But this one, yeah, I do like here this one for several reasons. I do like this one here best. But the important thing is that this is homogeneous. There are some upper bounds also have been proved. So HIMC of the permanent is bounded by M choose M half. This follows from Grenier's construction. And now you get a very, very nice reformulation of Valiant's original conjecture. This is the HIMC of the permanent is not polynomially bounded. So this is not the determinant complexity anymore. This is the HIMC, and this is a homogeneous way of measuring complexity. And yeah, so there has several advantages that.
Sorry,
yes.
Sorry. So once again, just to understand it, so you're saying you want large matrices, perhaps,
Yes.
with only these n squared variables, and you take n
No,
of
it's a
them,
lot of
multiply them
variables.
out.
It's n squared times d
Oh,
variables.
okay. Oh, n squared times d. Oh, okay,
Yes,
okay,
yes,
okay,
yes. A lot of
okay.
variables. It's yeah. So you also
Okay.
increase the number of variables.
You also increase the number of variables.
Yes,
Okay.
yes, yes,
Okay.
yes, yes.
Yeah. Yeah. Okay.
Yeah, yeah,
Yeah.
yeah. Yeah, you could also take just n squared variables if you want to, and take a dth power of your matrix. It's also possible to do that. What
Okay.
There are some slight issues with that because your polynomial will not be characterized by its symmetries anymore. But it's also possible to do that. This is what I try to like put in the footnote here for further reference.
Okay.
If people are interested,
Okay.
this is also possible. So there are several ways of doing this. This here seems to be the most natural one. And I'll show, I'll give evidence in a second also about that.
Okay.
Okay, so it seems to be conceptually simpler. If you do this in a homogeneous way, then there's no padding. Of course, I didn't tell you what padding is. I don't have time. I just tell you this is the better way of doing it. And also, it has not as many peculiarities, I call it. So all these results here, they don't hold in the homogeneous setting. So there are no useless types of representations. There are no strong occurrence obstructions, no-go results. Although we do know that the multiplicity obstructions are stronger than occurrence obstructions, also even in this setting, but nothing as strong as this paper about no occurrence obstructions. And there are also no surprising computability results. So these two papers here give very surprising results what can be computed, and it's very important that we are in an affine setting in these papers. But we want to do a homogeneous setting. Actually, it's also very classical to have a homogeneous setting, because Waring rank, for example, is one of the examples that has been studied in algebraic geometry for a long time, and that's a homogeneous setting. It's about homogeneous sigma wedge sigma circuits, and it's a useful testbed for GCT ideas. So the Waring rank is you have a homogeneous DVD polynomial, and you want to write it as a sum of dth powers of homogeneous linear polynomials. Again, homogeneous linear, or I just typo here. Oh, there's numerous typos on the slides. You've probably noticed so already. Okay, so you take homogeneous linear polynomials and you raise them to the dth power and you sum them up. And you want to get your polynomial. And the smallest r possible is called the Waring rank of your polynomial. Right? For example, 6x squared y. What's the Waring rank? So you can write 6x squared y as x plus y cubed plus y minus x cubed minus 2y cubed. Right? This is like, those are three summands. And the Waring rank, therefore, is at most 3. Actually, the Waring rank of 6 times x squared y, but the 6 doesn't really matter because you can pull the 6 inside of the cubes, right? So this is, Waring rank is invariant under rescaling, right? This is also a property because it's homogeneous. So in fact, the Waring rank one can prove is 3, and that is now interesting in the next example. The Waring rank of x squared y is indeed 3, so you cannot do better than this. Okay, so what did I wanted to say about other algebraic models of computation? So the conjecture can be phrased homogeneously, right? It's about a homogeneous complexity measure of the permanent growth superpolynomially. And the non-homogeneous settings, they have some peculiarities. And actually, the homogeneous setting actually has been studied classically in algebraic geometry. All right, so we focus on this HIMMC. This is the one that I want to discuss in this talk, and a bit on the Waring rank, because the Waring rank is a bit has the easier small examples, like this one here, for example. X squared y can be expressed as the sum of 3 cubes, as we've seen before. But now, if we draw like some kind of diagram that says, I mean, let's just say this is a set of all the polynomials that have a Waring rank at most 1, and here's some the Waring rank at most 2 polynomials and a Waring rank at most 3 polynomials, then this x squared y lies here at the boundary. And why is that? Because there's this sequence here of polynomials that have a Waring rank 2. And well, if you see, I mean, this has a Waring rank 2, obviously. It's parameterized by some epsilon that is non-zero because you divide by epsilon here. If you expand this, you see that indeed this polynomial converges to x squared y. but it has a Warring rank. I mean, these polynomials for every epsilon, they have a Warring rank of 2. So there's a curve here that converges to x squared y, and it's inside of the set of Warring rank at most 2 polynomials, and it converges to x squared y. Right, and what I mean by convergence here is defined on the or in this coefficient wise, right? So you just take the coefficient wise convergence here. All right, and that's an interesting thing, and it actually makes this determining the Warring rank actually really subtle, because I mean, you want to prove lower bounds, say on the Warring rank, but now if you have a continuous function that vanishes on all the whole set here of Warring rank at most 2, so it's 0 here everywhere, then it also means, because the function is continuous, let me assume it's continuous, it must also vanish on x squared y. What you would like to have is some function that vanishes on the Warring rank at most 2, but doesn't vanish on your point. So your point has a higher Warring rank, but this is impossible to get. There's no continuous function like this. And what algebraic geometers defined is the border Warring rank, because this is much nicer for them to study. It's the smallest n such that your polynomial can be approximated arbitrarily closely by polynomials of Warring rank at most n. So here in this example, since there's this curve and it converges to x squared y, so it approximates this point arbitrarily closely, the border Warring rank of x squared y is 2, while the Warring rank is actually 3. Right, so this is the very first border complexity measure. And this approach of border complexity measures, you can do this for many more complexity measures. So the main advantage of doing this, just not showing the curly braces here. So the main advantage is that if you look at the set of polynomials that have a border Warring rank of at most n, that is the same as the closure of the set of polynomials of Warring rank at most n. Right? So this set is closed. So it's guaranteed that the non-membership in the set can actually be proven by finding a continuous function that vanishes on the set, but does not actually vanish on the point. So if you don't have this closed condition, then you know that there will be some function. But if you have the closed condition, you know it's a continuous function. And now if you find more properties of this set here for the border Warring rank at most n, then you will find actually more properties of your separating functions. Here it's just continuous, but it gets more interesting. For example, let's look at Warring rank, or let's say border Warring rank at most 1 in some very tiny example, tiny vector space here. Let's look at the vector space of homogeneous degree 2 polynomials in 2 variables, x and y. That's just a 3-dimensional vector space. You have x squared, x, y, and y squared. This is your basis. And you want to look at a subset here, which I call x1. It's a set of polynomials that have a border Warring rank at most 1. Well, in this case, border Warring rank 1 is the same as Warring rank 1, but just for the sake of having an example with a border Warring rank. Okay, so those are the polynomials that can be written as a square. So there exist constants alpha and beta, such that your polynomial can be written as alpha x plus beta y squared. That can be written as a square. But not every polynomial can be written as a square. So some polynomials have a higher Warring rank, a higher border Warring rank. And now, what is a function that vanishes on this and that can be used for separating points from this? It's this is the discriminant. So if you look at the set here of Warring rank at most 1 is exactly this. It's the polynomials ax squared plus bxy plus cy squared, where the discriminant b squared minus 4ac vanishes. Now this is a continuous function that vanishes on your set, and you can use it to prove that something has a higher Warring rank than 1. So a very first lower bound, you can prove that the Warring rank of x times y is at least 2. Because what you do is you just, well, you look at xy. Well, xy means that b is 1 and a and c are 0. So you just compute b squared minus 4ac, but b squared minus 4ac is 1 squared minus 4 times 0 is 1, which is not 0, right? So therefore, the Warring rank here is at least 2. And that's a lower bound, right? This is the first lower bound. And such polynomials here, these polynomials b squared minus 4ac, these polynomials, and I will always use the letter f for them, they are called a polynomial obstruction, or also a separating polynomial. And yeah, as I said, if we find more structure, if we reveal more structure of these sets, then we can obtain more information about polynomial obstructions. And yes, we will do this. But let me say now, this is not just limited to Warring rank.
Can I ask a question?
Yes, please go ahead. Yes.
To this example, so this obstruction polynomial, it's now treated as polynomial of the variables ABC, right?
Yes. So this is exactly. So this is a function. B squared minus 4ac is a function on this space of polynomials. So the space of polynomials, you can think of this space here. Yeah, this is a bit subtle indeed. So this is a 3-dimensional vector space. And you can think of, it has 3 basis vectors, and you can call them whatever you like. You can, you can, for example, call them x squared, xy, y squared, and now it has every element here can be written in some unique way in this fashion. And you now on these coefficients, you now take polynomials in these coefficients. This is exactly true. So this is a different level of a polynomial, right? These are your normal polynomials, and you think of your normal polynomials as points here in the set. And these functions, these polynomials, have a very different feel. They are functions that describe properties, right? You can evaluate them at points here in this set.
This sounds to me like some kind of duality, actually.
There is a duality here. Yes. So formally, it's you take a polynomial ring over the dual space. That is true.
Okay.
But yes, this is correct.
Okay. Thanks.
Yeah, you're welcome. No problem. Yeah. Okay. But it's not. I mean, these two are not just. You shouldn't think of these two polynomials as dual to each other, but rather than these polynomials being points in the set, literally points in the set, and the other polynomials being functions on that set. Higher degree functions. It might be higher degree. This is degree 2, for example. Okay. So we do want to study these functions, and yeah. So this is indeed a subtle point here. That these are polynomials in these other in the coefficients of the original polynomials. And so this works not just for Warring rank. So when I give this talk, and sometimes I focus too much on Warring rank, and people think, oh, this was a talk about Warring rank, but it's not about Warring rank. This is a completely general thing. So I think there's a problem with like a black rectangle here, but I hope it's not too bad. So it says approximations also help in most other computational models. So you have any complexity measure that we talked about. We talked about these all different complexity measures. Then we can define a border complexity measure exactly, completely analogously, like we did for the Warring rank. And we usually give it like an underscore. And that is just the smallest n such that your polynomial can be approximated arbitrarily closely by polynomials where the complexity is bounded. So determinantal complexity, you can do the same thing, right? You can do exactly the same thing. And yeah, so this has been done, and it also has been studied. So very small cases have been studied. And Landsberg found a point P, like a polynomial. It's this polynomial here in 9 variables that indeed has a border determinantal complexity in this case of 3, but its determinantal complexity is not 3. It's higher than that. So there's a sequence here of polynomials, and he can write that sequence down so that the limit is P, but he can also prove that the determinantal complexity cannot be 3 or less. It must be higher than 3. So these things happen in other computational models as well. But here's another example where this polynomial is a degree 41 polynomial in 17 variables. We know from 2 papers, if you put these together, that the HIM the HIMMC bar, so the border homogeneous IMM complexity is 2, but the HIMC of the polynomial is bigger than 2. And you can have a simpler small example where you can see that this is also happening, is instead of the 1-1 entry, you take a trace. So if you take the trace of a bunch of 2x2 matrices here, and you put these entries, then if you let epsilon go to 0, you get a polynomial, but that polynomial cannot be written as a trace of a product of 3 2x2 matrices. But you need a product of 3 larger matrices. Note that all these things, what they have in common is that they have some kind of inverse power of epsilon somewhere, right? Because you are not allowed to set epsilon to 0. You have to take a limit process. So the computation will make these bad terms cancel, and then you can take a limit process. This is what always happens. Yeah, so this is a natural thing, happens to all the computational models that we have. But the main reason for doing this, because I mean, we're adding some kind of complication now with these epsilons, but the reason is now that this set is now closed. So the set of polynomials where this border complexity measure is bounded from above by n is now closed. And we will see that it has many more properties than just being closed. It's actually an algebraic variety and it has an action of the general linear group. If you do that, if you don't do that, you're losing all these properties. So this is why people do close their sets, and why people do define the border complexity measures. So if you do that, something interesting happens. If you say, okay, I mean, I have my usual 3 complexity classes of efficient algebraic computation, but now let me replace all these complexity measures by the corresponding border complexity measures, like polynomially bounded border formula complexity, or polynomially bounded border determinantal complexity, or polynomially bounded border circle complexity. You get 3 different complexity classes. And you can still conjecture that the permanent should not be in these classes. And that's a strengthening of variance conjecture. It was independently phrased in both Mourmellet-Zohony's paper and also in Burgess's paper in slightly different ways. So, but it's in both of these papers. And this conjecture now has an extremely nice phrasing, right? I mean, you can say, yeah, so VNP is not contained in VBP bar if and only if the border homogeneous iterated matrix compilation complexity of the permanent is not polynomially bounded. So border HIMMC of the permanent is not polynomially bounded. And that's an extremely natural measure of complexity, and it's homogeneous. So this is the nicest way, I think, of phrasing it. But it comes now with some interesting questions, actually. So these are the strengthenings of the conjectures. But the major open problems now are, they are also already highlighted in the 2001 papers, is that are these classes equal to their closure, or are they different from their closure? And actually in both papers, the authors say that, yeah, it looks fairly close to the original class if you put the closure, but it might also be different, right? It's not so clear that they don't boldly conjecture that these are the same. But it would be amazing if these are the same, because that would mean that the strengthened conjectures that we had, they are equivalent to Valiant's original conjecture, right? And that would mean that Valiant's original conjecture can now be actually attacked with actually all these methods that we have from algebraic geometry and representation theory. So we could work actually with the closed sets, but we don't know that. We don't even know if VF bar is still in VNP. So the closure could be extremely powerful, and but we just have no idea at the moment. Yeah, let me introduce a toy model where this is even open. So let me say V warring is a set of sequences of polynomials whose warring rank is polynomially bounded, right? In the same way that we defined the other classes. Even here, this question is open. Is V warring bar, is it equal to V warring? Even that is open. But there are some results in this direction. An old one by Nissan showed actually that HIMMC is equal to HIMMC bar in the non-commutative word. So in the non-commutative word, this is all fine and nice. So this is also one reason why I do like the HIMMC. And there's another result. We recently proved that the border warring rank is actually upper bounded by the HIMMC. But see, it is immediately clear that the border warring rank is upper bounded by the HIMMC. Well, so this here is not a measure that has an underscore, so it's removed. So the underscore here is removed, right? So it's a result of you have these epsilons and you can actually remove them in the process, and you have some upper bound from a complexity that does not actually have the approximations anymore. And this means that actually V warring bar is sitting inside VBP. Compare that, we don't even know if VF bar sits in VNP, so we don't even know that. But for V warring, it's actually, we are fine. We can actually do this. So this was discovered actually first by Forbes. But now I want to just highlight how natural it is to study HIMMC because of this very nice inequality, for example, and this one here. And so very recently also, it was, so this very strong paper came out where sigma k pi sigma circuit bar was shown to be in VBP. So there are some very nice results going forward in these directions. And yeah, I just list a lot of people that study in recent papers the power and the limitations of border complexity. But let me say, it's just still a mystery of what's going on. Okay, so the conjecture VNPs should not be in VBP bar is equivalent to this very nice conjecture about HIMMC bar of the permanent. And the set here is now closed of all polynomials that have an HIMMC bar less or equal to n. So proving can be done using continuous functions f that vanish on the set but not on the permanent. And now we will see that these are actually algebraic varieties, and this will allow us to impose more restrictions on f. So this is now about algebraic geometry. So what's an algebraic variety? Yeah, so hopefully the black rectangle doesn't hide too much of the sentence. If you have a vector space, and I wanted to have the dimension should be this eta here. And you can think of this eta as, for example, you take the vector space of homogeneous degree 2 polynomials in 2 variables, for example. That was eta was actually 3 in that case. So, I mean, that's the picture that we had about warring rank. So you have some subset here. For example, there could be the set of warring rank 1 polynomials. They're sitting inside. And so X is called an algebraic variety if there exist polynomials. And they're called, say, F1 up to F capital N, some finite set of polynomials, such that your X can be described as a common zero set of all these polynomials. That's the definition of an algebraic variety. And of course, if you have a set like this, then it's extremely nice to prove that something is not in the set, right? You just, something is in the set if all these functions are 0 at the point, and something is not in the set if one of the functions is not 0 at the point, right? So this means it's extremely nice to have that structure. Yeah, for the example, if you put eta to 3, then you can think of this set here, and of border warring rank at most 1, and this is exactly when the discriminant is 0, right? So this is one of the functions f1. Here it's actually a bit simplistic because there's only one function. So in general, you could have more functions that need to be 0 at the same time. And yeah, we know that by this very simple argument that these polynomial obstructions must exist, right? So if this is an algebraic variety and your point is not in Xn, then in the algebraic variety, then there must be some polynomial where your function is 0 everywhere, but your function is non-zero on your point, right? You just pick one of the functions here. It cannot be 0 on all the functions because otherwise the point's in the set, right? So we really want that all our sets are algebraic varieties, and we can actually do that. right? Yeah, this is a picture of where I want to try to highlight how this looks like. Will be useful later to think of it in this way. So say this is the set of polynomials or homogeneous degree 3, where the HIMC bar is at most 2. Okay, there's this set here, and these are vanishing sets here. So the red thing here is a vanishing set of a polynomial, and the blue is a vanishing set of another polynomial, and the green is a vanishing set of some polynomial. Of course, vanishing sets of polynomials do not look like this, right? It's just for set theoretic inclusion purposes only. And then this is the common zero set of all three here. And the permanent does not lie in there, right? So how do you prove that? You just take one of these functions, not the green one, but you say the red one or the blue one, and you just evaluate that at the permanent, get a non-zero value, and this proves the permanent is out of the set. Okay, just a remark that if you are using partial derivatives or shifted partial derivatives or any rank-based method to prove lower bounds, you are actually proving the existence of polynomial obstructions, because you will these polynomials that you will construct are actually determinants of minors of your matrices that you construct. Okay, that is just a remark. Okay, so we want to now really prove that these are algebraic varieties. So we have our algebraic complexity measure. I have to make some assumptions on that complexity measure, right? And I want to be vague here. I just want to say it's some complexity measure that's given by a syntactic circuit class, and the inputs are homogeneous linear, right? So we always have that basically. Then this is actually an algebraic variety. So a set of polynomials whose border complexity is at most n, that's an algebraic variety. And the proof approach is, so first observation is that this is indeed, if the border complexity is at most n, that's the same as closing the whole set. But yeah, that's just the first observation, because this is by definition of the border complexity measure, right? So this is already closed, right? It's like Euclidean closed. But now what we want is, we want things to be Zariski closed. So what is the Zariski closure? The Zariski closure of any subset of your space is the smallest algebraic variety that contains your set. So that's a bit coarser than your usual closure. So usually you have your set, you can close it, and then the Zariski closure might be even larger than that. So we want, of course, if this closure here would be equal to the Zariski closure, that would be amazing, because that would mean that this set is indeed an algebraic variety. So yeah, we want that. So if the closure is equal to the Zariski closure, that's perfect. And this is actually an algebraic variety. So we want that. Interestingly, this is not always true. This actually depends on your field. I think this example here is fairly instructive, actually. So look at this, the vanishing set here. Look at this curve. It's a curve defined by the equation y squared is equal to x times x plus 1 squared. And it's this curve here and that additional point. And now let's say your set y is just this curve here without the point. Well, then if you close it, it's still the curve. I mean, closing means like you're adding all the limit points. You're not adding any more points. So in particular, you're not adding this specific point here, because that's very far from your curve, right? But if you take the Zariski closure, you will see that you will actually add this point to the set. Because yeah, this set here, this set is not an algebraic variety. This becomes an algebraic variety by adding this point. So so the smallest algebraic variety containing this curve here is actually the one that actually contains also this point. So over R, these very subtle things happen, and there's a way around this over the complex numbers, and this can be concisely stated in the language of orbit closures. So I want to introduce what is an orbit closure, because we will need orbit closures anyway in further lectures. So might as well discuss them now in this setup. Okay, let's look at the polynomial x squared y. And this is the limit process that gives me x squared y. And now I want to now really work hard to put this into the format that is the sum of two cubes, right? So I want to convert the minus here to a plus by introducing a third root of -1, and I want to also take the scalar and put it into the cubes, right? So it's a bit ugly, but now it's really a sum of cubes, okay? Because if it's a sum of cubes, now I can write this in a different way. I can say, okay, this sum of cubes here is really just this polynomial here, x cubed plus y cubed, evaluated at these two linear polynomials, right? This is you plug in this for x, you plug in this here for y. This is the same. It's an evaluation of this polynomial. And you can rewrite this by saying, okay, this is the polynomial evaluated at, well, this is a row vector here of two things. And I can write the row vector in this fashion here by saying, okay, the left-hand side is just an xy standard vector here, just having the variables in it and a matrix. Right, so this is literally just a vector times matrix multiplication. And now I want to introduce this notation that people use for this. This is you take the matrix and you multiply it from the left to the polynomial. This is just notation now, okay? This is just a notation that will be used throughout the talk. This is what people call this group action on polynomials. But it's nothing complicated, right? It's just a different way of writing this. And you can now say, okay, well, I mean, might as well have a look at all the 2x2 matrices and apply them to x cubed plus y cubed. And this is, yeah, you could write it as this, all 2x2 matrices applied to x cubed plus y cubed. You get the set, like you take all the matrices, you apply them, you get a set that you see is indeed, this is the set of polynomials whose Warring rank is at most 2. Right, if you do that. Because, yeah, if you do this, you get a linear form here, and you get a linear form here, you add up their cubes, right? So you see that the set where the Warring rank is at most 2 is actually a monoid orbit. This is a monoid here, see this matrix monoid, and you apply it. So that's an orbit, it's a monoid, it's called a monoid orbit. But we already know that's not the correct way of defining things because we want to have the border Warring rank. Like x squared y is not in this monoid orbit, but x squared y lies in this orbit closure, right? Which is exactly describes the border Warring rank of most 2. Now, usually what people don't write it like this. People usually say, okay, it's nicer to use the group instead of the monoid. So GL2 lies inside C2x2 and is dense in there. So instead of using the whole monoid orbit closure, you can also just use the GL2 orbit closure here. And it's called now a group orbit closure. And that's the same set. So the question about having a border Warring rank at most 2 is now a question about membership in a group orbit closure. And that is great, right? It has just has a lot more structure now. Yeah, this is just how you formally define this, but this is basically, I think from this explanation is clear now. And yeah, so this means now if you have a complexity class, then yeah, then the set where the border complexity is at most n is basically described by orbit closures. Yeah, it's actually, there's some slight subtlety, but you can always think of just this is described by orbit closures. And the translation always works exactly in this fashion. Now, what does it help us? So this basically means that these sets, you can think of these sets as orbit closures. But now, yeah, we can invoke some nice theorems that these are constructible. So a set is constructible if it's a finite union, intersection, or complement of algebraic varieties, so some combination of those. And Chevaly's theorem tells us that orbit closures are always constructible. So I'm just sketching the proof here, not telling you exactly what these are, but we will discover them in later lectures. We will discuss these in later lectures. But for constructible sets, the Euclidean closure here, this closure is equal to the Zariski closure over C, right? So indeed, these things are algebraic varieties, right? So that is the sketch. And the fundamental conclusion is now, if you have any border complexity measure, then you can always prove the lower bounds using polynomials f that vanish on your set but don't vanish on your point. You can always do that. It's completely analogous to the discriminant. Yeah, so what is the complexity of these f? Just a remark, there's a recent high interest in the question of what is the circuit complexity of these f, but I don't want to go into that. And I instead want to discuss that they have even more structure. Since it's an orbit closure, it actually has an action of the general linear group, and I want to discuss that. Okay, so this set that we want to actually understand is the set of border IMMC being bounded by n. That's an orbit closure, and this means that if a lower bound is always a point, is not in an orbit closure. And we know the orbit closures are Zariski closed. So this means that a lower bound exists if and only there's a polynomial that vanishes on the orbit closure but doesn't vanish on the point. And now we want to study these f here that vanish on these orbit closures. We want to study them using representation theory. That's the last thing I want to talk about. I'll say, so this is a bit, yeah, okay. Consider what happens in the three-dimensional vector space of homogeneous degree 2 polynomials in two variables when we exchange the roles of x and y. Okay, so it's a three-dimensional vector space, but you have some kind of way of interchanging. Well, you're mapping x squared to y squared and vice versa, and x times y is just fixed. Because this is a linear endomorphism on this vector space, three-dimensional vector space maps to itself. And we already introduced the notation for this. It's you apply the transposition matrix to your polynomial. Well, this is just a notation. It's literally just exchanging the roles of x and y. So we say it's a representation. So this three-dimensional vector space is a representation of S2. Formally, this means it's a vector space with a group, and the group elements, they act on the vector space. And formally, they do this with a map that maps the group elements, each group element to a linear map. So here there's just a one linear map, basically. It's just the operation tau is just flipping the roles. And there's the identity group element is just not doing anything. It's just fixing all points. Right? So this is a three-dimensional vector space is a representation. And we find that x times y is actually invariant under exchanging the roles of x and y. And x squared plus y squared is also invariant under exchanging x and y. And we find that a third vector here that's linearly independent of the others, x squared minus y squared, is actually equal to y squared minus x squared. That is skew invariant. So we do have some decomposition here of our three-dimensional vector space into some invariance and some skew invariance. And this is a direct sum. And yeah, so these are sub-representations of the representation. So a sub-representation of a representation is a linear subspace that's closed under the group action. Indeed, of course, the subspace here is closed under the group action because the vectors are just, if you act with a group, all vectors are just scaled by a -1. And these here, if you act with a group element, the vectors are just staying the same. Right? Actually, each vector here, each vector has like its linear span on its own is already a sub-representation. And now there's if you just count here the dimensions of these spaces, we call this the multiplicity. So it's the multiplicity of the invariance. Here in this three-dimensional vector space is 2. And the multiplicity of the skew invariance in this vector space is 1. Or there's one skew invariant, there's 2 invariants. It's just counting here. And that's a very simple example with this three-dimensional vector space. The more interesting thing happens in the 6-dimensional one, where you're starting with your vector space that's three-dimensional with its basis here, x squared, xy, y squared, and you rename the basis vectors. So again, this is the same thing that this is basically the same thing that I discussed with Piotr's question here about these are the coefficients basically. And you can define the six-dimensional vector space of polynomials in these new variables. And you still have an action of, you still have an idea of what it means to exchange the roles of x and y. Because if you exchange the roles of x and y, x squared is mapped to y squared, right? So this means like a should be mapped to c and c should be mapped to a. And b should be fixed. And this is exactly what it is. So formally, this is how you can define it. And this is the resulting effect here. So tau of A is just C, tau of B will be B, and tau of C will be A. And tau of A squared, therefore, if tau of A is C, then tau of A squared should be C squared, right? You won't have an algebra morphism here. Tau of AB is BC because you switched the A with the C, you kept the B, right? The B is not changed. Tau of C squared is A squared. So on the six-dimensional vector space, you have now an action of this group S2. And you can, again, the six-dimensional vector space, search for the invariants and the skew invariants. And you find some. You find that these four here are all invariant, and these two here are skew invariant. And actually, this always works. So if you have any finite-dimensional vector space and you have an action of S2, it will always decompose into invariants and skew invariants. Here, the multiplicity of the invariance is 4, the multiplicity of the skew invariance is 2. Now, b squared minus 4ac, the discriminant, right? That one actually interestingly lies in one of the sites here. It lies here in the vector space of invariance. It could, yeah, in principle, it could be shared here among the two, but it's not. And it can never be, actually. So we will see this in a second. Okay, again, this is just our vector space with this basis here of these 6 polynomials of degree 2. And now we want to, instead of just looking at what happens if we exchange the roles of x and y, we want to allow all linear transformations, like any element of GL2 should be allowed to act now, instead of just having the transposition matrix, every element of GL2. So this is a formal way of defining it. I think an example is the easiest way of doing it. If you have this matrix here and you apply it to x squared, well, this matrix says this matrix here says that you replace x by y and you replace y by x. Right? So this one says you replace x by x plus y and you keep y. So if you apply that to x squared, you get x plus y squared. You get this polynomial here. Right, and so again, you rename the basis vectors. So if you apply to A, you get A plus 2B plus C. Now, this is just renaming the basis vectors so that you can now, for these higher degree polynomials, actually have an action on these higher degree polynomials. So if you know that this is how it works on how it acts on A, then this is how it acts on A squared. Right, so you just plug it in, you square it, you get this more complicated polynomial. In fact, yeah, so this action, or yeah, it will always be, yeah, gives quite a complicated action actually to compute these things. Not so, yeah, it gets a bit involved, and these terms usually get very long. But sometimes it's really nice. So for example, if you have an upper triangular matrix here, and you apply this to A squared, then, well, A squared is the coefficient here of x squared. But this matrix says you keep x invariant and you're only doing something with y. So this means that this fixes A. So it also fixes A squared. Right? So nothing happens here. And a bit longer computations shows that if you take the discriminant and you act with a 2x2 matrix, then this actually just rescales the discriminant by the determinant of G squared. Well, that's a bit of a longer computation. So you decompose your 6-dimensional vector space into a 1-dimensional and a 5-dimensional here. And both of them cannot be further decomposed into subrepresentations. So they are called irreducible. So you have an irreducible subrepresentation here, and you have an irreducible subrepresentation here. And this also always works. So the theorem is that GLN is reductive. So whatever you do, any finite dimensional representation of GLN, which this is here, you have an action of GLN. It can always be decomposed into a direct sum of irreducibles. And that is very good, because now what you want to do is you want to study what is the representation that you want to study. It's the vanishing ideal. So let me tell you what the idea is. So again, our example is the three-dimensional vector space, and we want to study this polynomial ring in these other variables a, b, c. And again, take our x, for example, Warring rank 1 polynomials. What's the vanishing ideal? So the vanishing ideal of some set is just the set of polynomials it's the set of polynomials that vanish on the set. That's just it. You take them all and you call this the vanishing ideal. It's exactly the polynomials we want to find, right? It's the ones that vanish on the whole set. You can use, if you have a function in the vanishing ideal, you evaluate at a target point, and if it's non-zero, then this means that your target point is outside of the set. So those are the desired polynomials that we can use for separating polynomials. And you can also do this in degree D if you want to. That's a subtlety. This is a cone. Don't worry about it. And so the vanishing ideal is a subrepresentation, and that's crucial because we are dealing here with orbital closures. The vanishing ideal will always be a subrepresentation, and that's amazing because this means our vanishing ideal is a representation. We can decompose it into irreducibles, right? For example, again, this is the decomposition that we know, and the vanishing ideal is not by accident. It's just consists of b squared minus 4ac. This is one of the two parts here, because it must be a subrepresentation. So it must be some kind of it's very restricted what it can actually be. In this case, it could only be like this thing here or that thing. It could be both or none of them, right? But it turns out to be b squared minus 4ac. Makes the search, of course, for these much easier. And now so the conclusion is now that, so all the lower bounds, they can not only be proved by a separating polynomial, but it can actually be a separating polynomial in an irreducible subrepresentation of the vanishing ideal. And that is great because we do understand actually these polynomials in the irreducible subrepresentations much better. And those are highest weight vectors. Let me tell you what that is. So b squared minus 4ac, what's so special about this b squared minus 4ac that it's able to actually cut out this variety? It's a highest weight vector, and that is just a polynomial that if you act with a diagonal matrix, it rescales the polynomial. So here, if you think of G being a diagonal matrix, having just alpha 1, alpha 2 on the diagonal, and you act on b squared minus 4ac, you rescale it by the determinant squared, which is alpha 1 squared times alpha 2 squared. So here this would be lambda 1 is equal to lambda 2 is equal to 2. That would be what happens to the discriminant. And also you want it to be invariant under the action of upper triangular matrices with ones on the main diagonal. And these vectors are called highest weight vectors, and every irreducible contains exactly one of them up to scale. So instead of the irreducibles, you can also study the highest weight vectors. So they are two irreducible GLN representations are called isomorphic if they're the weights of the highest weight vectors, they coincide. So b squared minus 4, this also means that there's an isomorphism actually between the two representations. B squared minus 4ac is a highest weight vector, as I outlined here, where the weight is 2, 2. And a squared is the other highest weight vector in the 6-dimensional vector space, and the weight is 4, 0. Right? So here you find an irreducible of type 2, 2, and here you find an irreducible representation of type 4, 0. And the vanishing ideal actually in degree 2 only has an irreducible of type 2, 2. And this means that lower bounds can always be proved using highest weight vectors. you take a highest weight vector, and this is like a random matrix G. You move the highest weight vector, put it in a general position, and those functions are enough to separate, to prove all these border complexity lower bounds, always. And that is, of course, great. But it might be difficult to work with the highest weight vectors directly. So Mommel and Zerhony proposed to circumvent working directly with them, but only working with the multiplicities. And that's the number of isomorphic copies of irreducibles in a representation, because that is independent of the decomposition. You have a representation, it always decomposes into irreducibles. And the decomposition might not be unique, but the number of isomorphic copies of the different types, that is actually independent of the decomposition, and that's called the multiplicity. So here, the multiplicity, this is our example, multiplicity of 2, 2 in this vector space is 1. This is it, right? We find it once. We find a 4, 0 here, it's also 1, right? We don't find a 3, 1, so the multiplicity is 0. And for the vanishing ideal, the same, right? We have multiplicity of 2, 2 actually disappears, and the 4, 0 does not appear. And so these ones here, just a remark, these are actually, these numbers here for the polynomial ring are called the plethysm coefficients. And the vectors where this plethysm coefficient is positive, they give points in a moment cone. So we might see this in later talks. All right, we want to show, so how do multiplicities help? So we want to show the permanent is not actually in this orbit closure of IMM. Okay, that's the task. Then the first observation is that a point is in the orbit closure if and only if its whole orbit closure lies inside the other orbit closure, because that is because the orbit closure is the smallest set that's closed under the group operation and also topologically closed. This means that we can use the following approach. If there exists some lambda where the multiplicity in the vanishing ideal of the IMM side is bigger than the multiplicity of the vanishing ideal of on the permanent side, then there must be some highest weight vector that proves the permanent does not lie in there. And those are called multiplicity obstructions. And this is just by counting, right? There must be some highest weight vector that vanishes here, but doesn't vanish here, right? Just by counting how many there are. And the major open question is that, is this fine enough to prove strong lower bounds? And we don't know that yet, but in principle, there could be some issue, right? It could be that you have that the permanent orbit closure does not lie in the IMM orbit closure, but you cannot see it with the multiplicities. This might happen. So here's an example of how this might look like. Because these two situations, they look the same from the viewpoint of just multiplicities. So here's the permanent is inside the orbit closure of the IMM, and here's outside. But you see how many functions are vanishing on the IMM. It's 1 in both pictures. And how many functions are vanishing on the permanent? It's 2 in both pictures, right? So yeah, the multiplicities itself, they don't really tell you in which situation we actually are. This problem cannot occur if all highest vectors of a certain weight vanish on the IMM orbit closure. So this means like the vanishing ideal is, the multiplicity in the vanishing ideal is as high as possible. And if that's the case, then we call this an occurrence obstruction, if this is bigger than for the permanent. In that case, it's an occurrence obstruction. That's a very special type of a multiplicity obstruction. Yeah, so the occurrence obstruction approach for the determinate versus permanent does not actually give superpolynomial lower bounds. We do know that, but that is not a homogeneous setting, right? It's very important in that proof that we're using the constants. And we don't have a strong setting, a strong result like this in any homogeneous setting. And we do know occurrence obstructions actually can prove lower bounds on the border rank of the matrix multiplication tensor, and that's a homogeneous setting. And but we also know that there are indeed settings where the multiplicity obstructions are provably stronger than the occurrence obstructions. And there's some hope that the multiplicities might be fine enough. Well, there's a paper by Larson and Pink from 1990, and the more recent one by Yu that gives some hope that this might be actually enough to look at the multiplicities, but it's actually still fairly far from the result that we want to have. And there are situations where you can actually construct multiplicity obstructions by just using the symmetry groups of the 2 points that you want to look at. For example, if you want to look at permanent and IMM, then you can just look at the symmetry groups. But here, of course, in this paper, we only do this in a toy model. We are actually able to do this. And for that, you have to look at this is the last concept I want to just quickly mention is the coordinate ring. So for that result here, you have to look at the coordinate ring. And the coordinate ring is just, you take the whole polynomial ring and quotient out the vanishing ideal. Right, this is just the whole thing. This is the coordinate ring. And the multiplicities in the coordinate ring are very easy to understand. It's just you take the plethysm coefficient, like the whole multiplicity, and you subtract the multiplicity in the vanishing ideal. So it's not really clear what is the better viewpoint, if the vanishing ideal or the coordinate ring, because those are kind of dual to each other. But the coordinate ring has some interesting properties. And so I just want to say that some very interesting things are going on if you want to find out more about these multiplicities. And I just want to mention this. In many cases, the coordinate ring actually has a localization that can be studied using the algebraic Peter-Weyl theorem, which we might discuss in this lecture series, and representation theoretic branching rules. So this orbit closure that we want to understand, its localization at a fundamental invariant is the coordinate ring of the orbit, which is the coordinate ring of a quotient, which is the coordinate ring of the group taking the stabilizer invariants. And so we will discuss some of these concepts. And then this coordinate ring is actually understood. So its representation theoretic structure is completely understood. So this gives, so you can implement the complete approach and actually do find in some toy model that this gives actually multiplicity obstructions. So in the end, this means like this multiplicity is indeed just a dimension count of something that is not so difficult to understand. So this S lambda is an irreducible, we know explicit bases, we know the stabilizers. So these things, computations can oftentimes be done. All right, let me summarize. There are several definitions of how you want to define algebraic complexity, and then some are affine and some are homogeneous. The VBP versus VNP question, it can be naturally phrased in a homogeneous way using the HIMMC of the permanent. And this simplifies the transition to GCT. It's just going to IMMC bar and then seeing that this is an orbit closure. So when studying border complexity over C, this enables us access to some rich set of tools from algebraic geometry and representation theory. But it also raises questions when you go to the border complexity. So is VBP equal to VBP bar? In other words, are these two complexity measures polynomially related? And yeah, so this is a question, the conjecture now becomes a question about containment of orbit closures. And all the border complexity lower bounds, we know because of, since we are talking about orbit closures, we know that the lower bounds can be proved using highest weight vectors. If those are, yeah, those might not be so easy to understand, the highest weight vectors directly, so one can circumvent actually having to compute them explicitly. By just studying the multiplicities, we don't know if this is fine enough or not. So the highest weight vectors are certainly fine enough, but we don't know about how fine the multiplicities are actually. So that's just an open question still. And sometimes you can even just use the symmetry groups of the 2 points in question to find multiplicity obstructions, to separate two orbit closures. Yeah, so multiplicity obstructions are provably stronger than occurrence obstructions, but actually even occurrence obstructions, they do work in some cases, so we don't know exactly what are the limitations yet. Yeah, thank you very much for your attention and your questions during the talk. So I think we do stop the recording.
Yeah. Thomas, will you